Alright, welcome now to Chapter 9 on asteroids, comets, and the dwarf planets. Our goals for asteroids and meteorites discussion will be: what are asteroids like, why is there an asteroid belt, and how are meteorites related to asteroids. So what are asteroids like? Here is one. This is Ikuta. This was a mission by the Japanese to land on an asteroid and do a return sample back to Earth. And you can see it very dusty and grainy. Asteroids leave trails in long exposure images because of their orbital motion around the sun, and this is how we can help discover them. Here's some asteroid facts for you. Asteroids are rocky leftovers of planet formation. The largest asteroid is Ceres, about 1,000 kilometers or 600 miles across. There are 150,000 listed asteroids in catalogs, and probably over 1 million with a 1 kilometer diameter or more. Smaller asteroids are more common than large asteroids, and all the asteroids in the solar system would not add up to even a small terrestrial planet. So you can see by these pictures that the asteroids are cratered and are not round, because they do not have enough gravity of their own to be round. Here's a rather large one that is pretty round, Vesta, from the Dawn spacecraft. And we do have some asteroids that have their own moons. And so here is asteroid Ida with a tiny moon named Dactyl. Well, we know that the asteroids are between Mars and Jupiter. Well, why is there an asteroid belt there? Well, most asteroids are between Mars and Jupiter. There are some Trojan asteroids that follow Jupiter's orbit, and some orbits of near-Earth asteroids crosses Earth's orbit, and we need to watch out for those. So rocky planetesimals early on between Mars and Jupiter did not accrete into a planet, and Jupiter's gravity, through the influence of orbital resonance, stirred up asteroid orbits and prevented their accretion into a planet. So how are meteorites related to asteroids? Most meteorites are pieces of asteroids. So a meteorite is a rock from space that falls through Earth's atmosphere. A meteor is the bright trail left by a meteorite. What is a meteor wrong, you say? Well, that's just a rock on the ground. I cracked myself up. Okay. Meteorite types. Primitive. Unchanged in composition since they first formed 4.6 billion years ago. Processed are younger and have experienced processes such as volcanism or differentiation. A few meteorites arrived on Earth from the Moon and from Mars. The composition differs from the asteroid fragments, and this is a cheap but slow way to acquire Moon rocks and Mars rocks. So what did we learn? We learned that asteroids are rocky leftovers from the era of planet formation, and there's an asteroid belt due to Jupiter's orbital resonances. Most meteorites are pieces of asteroids. Primitive meteorites are abundant of solar nebula, and the processed meteorites are fragments of larger bodies that underwent differentiation. Comets, my favorite topic to talk about. How do comets get their tails, and where do comets come from? Now here's what we see if you're paying attention to the lecture. This is Comet Hyakutake in 1996, and this is my big claim to fame. This is a picture I took as a 19-year-old sophomore in college at Missouri State University, and this is from a wide field telescope that was at Kitt Peak National Observatory in Arizona. During the week of closest approach, this comet got 9.3 million miles away from Earth, and that was extremely close. Well, how do comets get their tails? Here's another picture of Comet Hyakutake, most likely taken probably the same night mine was. Well, we know that comets form beyond the frost line. Comets are icy counterparts to the asteroids. The nucleus of a comet is likely a dirty snowball. Most comets do not have tails, until they get close to the sun, that is. Most comets remain perpetually frozen in the outer solar system, and only comets that enter the inner solar system grow those tails. So the nucleus is like a dirty snowball, It's the source of material for the comet's tail, and there are two tails. A plasma tail that goes straight out, and a dust tail that kind of hangs on to the orbit behind the comet. The coma is an atmosphere that comes from the heated nucleus, and the plasma tail is gas escaping from the coma pushed by solar wind, and the dust tail is pushed by photons. Now, a mission I had a great deal to do with in the 2000s was Deep Impact, and the chief scientist for this mission was out of Maryland, and I had met him when I did the Comet Hyakutake study in the 1990s. And so I was part of this mission, and this is a spacecraft that had a projectile that hit a comet. And so this is Temple 1, and you can see in this picture the impact of the projectile onto the comet. Beautiful picture. Man, we got a lot of information out of this one. This hit July 4th, 2005. Well, comets eject small particles that follow the comet around its orbit and cause meteor showers when the Earth crosses that comet's orbit. And we see a meteor shower about once a month. Meteors in a shower appear to emanate from the same area of the sky because of Earth's motion through space. So where did the comets come from? Well, only a tiny number of comets enter the inner solar system. Most stay far away from the sun. And the Oort cloud and the Kuiper Belt is where the two come from. Comets in random orbits extending to about 50,000 AUs are from the Oort cloud. That's where Hyakutake came from. And the Kuiper Belt have a lot closer comets, 30 to 100 AUs, in more orderly orbits. And this is where Halley's Comet came from. Well, how do they get there? The Kuiper Belt comets come from the Kuiper Belt. Flat plane is it's a flat plane aligned with the plane of the planetary orbits, orbiting in the same direction as the planets. The Oort cloud comets were once closer to the sun, but when they were kicked out farther by gravitational interactions with the Jovian planets. How do comets get their tails? They're like dirty snowballs. Most are far from the sun and do not have tails, and the tails grow when the comet nears the sun and the nucleus heats up. Where do comets come from? The Kuiper Belt and the Oort cloud. Now let's go to a little more controversial topic on Pluto. How big can a comet be, and what are Pluto and other large objects in the Kuiper Belt like? Pluto's orbit is tilted and significantly elliptical. Neptune orbits 3 times during the time Pluto orbits twice, and this resonance prevents any kind of collision. The big question is Pluto a planet? And this lecture is being recorded in March of 2015, and in a few months we're going to fly by Pluto with the New Horizons spacecraft. We'll learn a lot about that. So, it's much smaller than the 8 major planets. It's not a gas giant like the other planets in the outer solar system. It has an icy composition like a comet, has a very elliptical inclined orbit, and Pluto has more in common with comets than the 8 major planets. In the summer of 2005, astronomers discovered Eris, an ice ball even larger than Pluto, and Eris even has a moon, Dionesia. There are many icy objects like Pluto on elliptical inclined orbits beyond Neptune. The largest one of these is comparable in size to the Earth's moon. So, are these very large comets or very small planets? Well, in a very controversial move in 2006, the International Astronomical Union decided to call Pluto and objects like it dwarf planets. So, what is Pluto like? Its largest moon, Charon, is nearly as large as Pluto itself, probably made by a major impact. Pluto is very, very cold and has a thin nitrogen atmosphere that refreezes onto the surface as Pluto's orbit takes it farther from the sun. Now, Pluto has 5 moons around it, maybe making it more of a candidate to be a planet. And in 2015, the IAU will revisit this vote they took on Pluto's candidacy for a planet. So we know that the New Horizons spacecraft will be visiting Pluto in 2015. Cosmic collisions. Impacts on the Earth. I'll make this pretty quick. Did an impact kill the dinosaurs? How great is the impact risk? Did an impact kill the dinosaurs? We know that small objects impact all the planets every day. You might remember a impact of a meteorite in Siberia in Russia a year or two ago. Evidence suggests larger impacts are also still occurring, such as the impact of Comet Shoemaker-Levy 9 into Jupiter in 1994. And that was 20 years ago, and I was actually doing research on this comet at the time, before I did the Hyakutake study. Take a look at this. This is a very famous impact sequence. This comet, named after Gene Shoemaker and his wife, and David Levy, broke apart when it went around Jupiter and went into a string of pearls, 21 comets long, little bitty comets. And so the tidal forces broke it up. We have seen this before. We see these crater chains on Callisto, probably came from another comet that did the same thing. And this comet actually impacted Jupiter over the summer of 1994. A very good friend of mine, Dr. Heidi Hamel, a young scientist at the time, used the Hubble Space Telescope to observe it. And every observatory around the world was trying to observe this at the time. Where I was at the Missouri State University Baker Observatory with a 16-inch telescope, I got time that week to study it. We only had one clear night, and there was only one impact scheduled, and we saw nothing from the impact. I later found out, years later, that that impact of that fragment meant the fact we didn't see it, I didn't see it, was an indication of the size of the impact being less than half a mile wide. So this impact left a black eye on Jupiter, and it stayed there for a couple of years. So here are several impact sites on Jupiter. And this is from an infrared telescope in Hawaii. Brilliant. And this is, you have to remember, this is in the early stages of the World Wide Web. And NASA tried to mirror websites that would show this, and one day 600,000 visitors went to NASA's website and the whole internet crashed. That's how early on this was, 1994. Mass extinctions. Fossil records shows occasional large dips in the diversity of species of mass extinctions, and the most recent was 65 million years ago, ending the reign of the dinosaurs. How do we know this? There's an iridium layer. Iridium is a very rare on Earth. It's surface rocks, but is often found in meteorites. And Alvarez found a worldwide layer containing iridium laid down 65 million years ago, probably by a meteorite impact. And all the dinosaur fossils all lie below this layer. So you can see right here, a layer rich in iridium, and so it tells us a huge impact occurred at this point in geological and biological history right here. And it's usually about an inch or two tall. While the dinosaur fossils lower in the lower rocks. So a meteorite 10 kilometers in size would send large amounts of debris into the atmosphere. That debris would reduce the amount of sunlight reaching Earth's surface, and the resulting climate change may have caused mass extinction. The likely impact site for this is the Chicxulub crater in the Yucatan of Mexico. Well, how great is the impact risk? This picture was taken from the Tunguska region. So in 2004, the Opportunity rover provided strong evidence for abundant liquid water on Mars in the distant past. But how could Mars have been warmer and wetter in the past? And well, clumps of rounded pebbles discovered by Curiosity, the most recent rover, compared with the sonar formations in Earth's stream. So asteroids and comets have hit the Earth. One of my former NASA interns was the one that landed the Curiosity rover there. When? And major impacts are very rare, thankfully. So a magnetic field may have preserved an early Martian atmosphere. Solar wind may have stripped the atmosphere after the field decreased because of interior cooling. And so here is that Russian
So we have
meteorite
learned that geological features tell us that water once flowed on Mars.
Asteroid
Dry riverbeds, eroded craters, and rock-strewn floodplains all show that water once flowed on Mars. Now Mars today has ice, underground water ice, and perhaps even pockets of underground liquid water. Why did Mars change? Because the Mars atmosphere must have once been thicker for its greenhouse effect to allow liquid water in the surface. Somehow Mars lost most of the atmosphere, perhaps because of a declining magnetic field.
And here's Meteor Crater, Barringer Meteor Crater in
and now on to Venus,
Arizona,
a hot world.
East of Flagstaff.
Venus is geologically active, and why is Venus so hot?
School bus. It's
we see a lot of volcanoes and lava flows on Venus.
3/4 mile wide, and you can go visit.
There are impact craters. There are very fewer than the Moon, Mercury, and Mars. Many volcanoes, and fractured and contorted surface indicates that the Arctic stress is on board.
I can tell you that the number of
now the Soviets landed Venera spacecraft twice on Venus, and the photos quickly they were taken because the spacecraft melted pretty quickly. The photos of the rocks taken by the lander showed little erosion.
We haven't seen it yet.
So does Venus have plate tectonics? Most of the Earth's major geological features can be attributed to plate tectonics, which gradually remakes the Earth's surface. But on Venus, they do not appear to have plate tectonics. The entire surface seems to have been repaved 750 million years ago. So why is Venus so hot? The greenhouse effect keeps its surface at 470 degrees Celsius, about 900 degrees Fahrenheit. Why is the greenhouse effect on Venus so much stronger than on Earth? It's because the atmosphere is 90 times as thick as that of the Earth and is very thick in carbon dioxide, which you remember now is a greenhouse gas. The thick carbon dioxide atmosphere produces an extremely strong greenhouse effect, and the Earth escapes this fate because most of its carbon and water are in the rocks and the oceans. The reflective clouds contain droplets of sulfuric acid, acid rain. The upper atmosphere has fast winds that remain unexplained. What unique features of Earth are important for life? Number 1, surface liquid water. Number 2, atmospheric oxygen. 3, plate tectonics. And 4, climate stability, a very important one. So surface liquid water, Earth's distance from the sun, and moderate greenhouse effect make liquid water possible. And where we find water, we find life. The oxygen creates photosynthesis, which is required to make high concentrations of oxygen, which produces the protective layer of ozone. The plate tectonics is an important step in the carbon dioxide cycle. We see continental motion around the Earth. Motions of the continents can be measured with GPS now. The idea of continental drift was inspired by a puzzle-like fit of continents. The mantle material erupts when the seafloor spreads. And so the seafloor is recycled through a process known as subduction, when plates go underneath each other and reheat the rock. And so the plate motions tell us a past and future layout of continents. The carbon dioxide cycle tells us the atmospheric carbon dioxide dissolves in rainwater. The rain erodes minerals that flow into the ocean, and the minerals combine with carbon to make rocks on the ocean floor. Subduction carries the carbonate rocks down into the mantle, and then the rock melts in the mantle and outgasses carbon dioxide back into the atmosphere through volcanoes. So the whole question about long-term climate change. The changes in the Earth's axis tilts might lead to ice ages. Our axis is now 23.5 degrees, but does vary a degree or two in either way. Widespread ice tends to lower global temperatures by increasing Earth's reflectivity, and carbon dioxide from outgassing will build up if oceans are frozen, ultimately rising global temperatures again. And the climate stability, the carbon dioxide cycle acts like a thermostat for Earth's temperature. So these unique features are intertwined. Plate tectonics creates climate stability. The climate stability allows liquid water. Liquid water is necessary for life, and life is necessary for atmospheric oxygen. And so all these connections are made. But how is human activity changing our planet? This is a plot of the temperature above or below the 20th century average global temperature. And you can see that the last decade here has been the hottest on record. In fact, we have globally about 350 months consecutively in a row that have been the hottest months ever recorded. And 2014 was indeed globally the hottest year on record globally. The dangers of human activity are human-made chlorofluorocarbons, CFCs, in the atmosphere. They destroy the ozone, reducing the protection from UV radiation. Human activity is driving many other species to extinction. And human use of fossil fuels produce greenhouse gases that can cause global warming. Earth's average temperature has increased by 0.5 degrees Celsius in the past 50 years, which doesn't sound like much, but it really is. The concentration of carbon dioxide is rapidly rising, and an unchecked rise in greenhouse gases will eventually lead to global warming. So here we see a plot of concentration of carbon dioxide since the 1960s, and we can see that it has gone up significantly. Now we can go back into ice cores and see that we have peaks in carbon dioxide activity, but since 1750, we've had an enormous spike in carbon dioxide. And the reason is the Industrial Revolution. We started putting out that gas into the atmosphere. So global temperatures have tracked carbon dioxide concentration for the last 500,000 years. And the Antarctic ice bubbles in the ice indicate the current carbon dioxide concentration is at its highest level in at least 500,000 years. Pretty remarkable. Most of the carbon dioxide increase has happened in just the last 50 years. Amazing. So we can model climate change, and the models of global warming that include human production of greenhouse gases are a better match to the global temperature rise. What makes your planet habitable? Located at an optimal distance from the sun for liquid water to exist. The life zone, or also called the Goldilocks zone. Has to be large enough for geological activity to release and retain water in the atmosphere. Earth is habitable because it is large enough to remain geologically active and is just at the right distance from the sun so oceans could form. We call that the Goldilocks zone, where life exists. So we know that unique features on Earth are important for life: surface water, atmospheric oxygen, plate tectonics, and climate stability. Human activity is releasing carbon dioxide into Earth's atmosphere, increasing the greenhouse effect and producing global warming.